in Sorin Tech. If you want to know more about me, I've been working as a digital nomad in the past few months. Right now, I'm giving this speech in Madrid. In this talk will be dedicated to a technology called Splunk. If you don't know what it is, don't worry, because no previous knowledge will be assumed. And so a few words of where I'm coming from. I've had the opportunity to work in some Splunk related projects with different customers. And recently I've acquired 2 certifications on Splunk. So I will share my slide right now. So what is Splunk? So it's a tool that basically eats up any kind of data and spits out dashboards, alerts, and knowledge objects of various types, as you will see. This is the agenda of the talk. Before defining what is Splunk, we will give a brief overview of the general context of big data and compare the traditional approach to manage data to the Splunk approach and how this maps to the technical components. And we will also list advantages and disadvantages. Then we will give a presentation of Splunk, its features, and its architectural components. Splunk Cloud will also be thrown in the mix here. Suggested topology for a successful deployment of Splunk will also be analyzed. And following that, then we present the common pipeline that someone who finds himself working with the product will typically implement in his first project. So the pipeline, as we will see, is composed of many steps: forward, index, search, data enrichment, dashboards, and alerts. Finally, we will talk about additional features which sits on top of Splunk, which is the machine learning toolkit, which makes dealing with artificial intelligence in Splunk very easy. There are many different so-called premium apps in Splunk, each suited for a different use case, from observability to monitoring of infrastructure, monitoring of apps, security, and behavior analytics. We won't be able to talk about those in this talk, but further reading will be provided. A few tips as well will be shown for some topics for the Splunk initiated, so someone who already knows a bit of Splunk. 2 simple use cases will be presented to illustrate how we can leverage Splunk to discover knowledge in quite any field. And the 2 example datasets that we find here are COVID tweets and Bitcoin transactions. So let's start. One of the main problems companies have to face nowadays is the problem of big data. And parallel to this, a new need arises to extract a knowledge that is actionable from a variety of different data sources and categories of information. IoT, cloud data, smart tech, AI are just the most modern form this data takes. The need is often twofold. So from one side, to make sense of this data, and from the other side, often to relate it to other data. And this can be achieved by collecting data into a single source of truth, where it can be actionalized. And with actionable data, we mean building knowledge objects, dashboards, alerts, and in general, anything that can provide value to stakeholders utilizing this tool. So the question here is how to convert all the data I have into something actionable, and preferably in a single place. So the IT infrastructure we usually see is this one. We have different layers, each composed of different technical components of what we call an IT service. And a service can be any set of interconnected applications and hosts that are configured to offer a specific service to the organization. But it is not to be thought of as a fixed thing, since it is defined based on the needs of that particular customer or user of the tool. Examples are both internal and external. We have internal examples like emailing systems, or external like an organizational website. So we require a lot of different components for a single server. As you can see here, there's web servers, databases, middleware, network infrastructure, hardware, and so on. And usually, from analytic purposes, each of these layers is isolated from the other ones. So typically, logs from each layer are stored in in different places and analyzed with different tools, and this makes it very hard to relate them. There are some of disadvantages of this approach. There's no end-to-end awareness across technologies, like I mentioned. High costs, because usually the cost is spread on all these different tools and infrastructures, which drives the cost up. Slow incident response, because different teams have to work together, typically with no knowledge of the full pipeline to come up with a solution. The choice of database is also usually suboptimal. Relational ones are not suited for unpredictable data like the one we're considering here. And an increased set of technology also means an increased probability of changes, which drives never-ending integration. And finally, it requires a massive scale. So compare this to the Splunk approach, how it is called the holistic model. And all layers here are interconnected. Logs from each layer are pushed into Splunk, where they are easily analyzed and related. Some advantages include a quicker incident response. So a single Splunk team can make a deep dive into the different kinds of data and find a solution earlier. Increase also situational awareness across layers, because this increased awareness can be enjoyed not only in the case of a problem, but for example, it enables a proactive approach to discover new opportunities and deepen our understanding of the interrelational properties of the data. And more on the business side, it lowers the cost risk, since if we have a lower number of components, then we have less integration to do. Well, vendor lock-in here might be a counter-argument. We also have more adaptability, because with Splunk we can take a sort of lazy approach. So we just ingest all data without worrying in the first moment, and then as the data, let's say, unfolds and we work with the data, we start to come up with interesting questions to ask. This is somewhat of a dramatic shift from the usual data analysis way, but it's useful to think about it. And AI and ML can always be employed with custom code and pipelines. The nice feature here is that we have them out of the box, as we will see. Let me explode one of the points that I made earlier, because it's quite important for our purpose. Classical database systems are not suitable for unstructured data. Keep in mind that all different applications we discussed about at the beginning typically need data that doesn't come in one format. For example, for a machine learning model, we would need audio files, video files, syslogs, web data, and basically anything to train it. Dealing with that with the relational database, let's say, is not the best of ideas. Cloud data lakes are more suitable. And the proposal of Splunk is the Splunk Machine Data Engine, which contains time series unstructured data. It is multiple domain. It doesn't have a predefined schema. It's schema on the fly. It can deal with the massive volume by retaining its speed, thanks to some magic tricks that we will see in due time. So what is Splunk? This image is taken from the official documentation, and it's a view of the basic features. We have data from different sources. We see on-premises, private and public cloud of different type, web servers, databases, smartphone, GPS, literally anything, and of different volumes. For example, with Splunk Cloud, we can get adaptive volume. And all of this is ingested into the Splunk Machine Data Engine in real time. And the actionable part comes with searches, dashboards, alerts, and everything that you see in this image. So before coming to the exciting part of knowledge discovery, we have to talk about the Splunk architecture and its component. There are 4 basic components. A forwarder is responsible for the data ingestion. It can ingest data from any source to remote Splunk indexers. And it has more capability than a simple network feed. For example, data routing and load balancing. There's a light and heavy version that we will discuss about in a few moments. An indexer is how Splunk stores and processes data. And during search jobs, indexers are also called search peers. A search head, on the other hand, is responsible for decomposing search strings into centralized and distributed parts, and send the distributed parts to to search peers or indexers. Then it consolidates the results fetched from the different indexers and displays the result. Usually, forwarders are distributed across many different servers, and it would be very annoying to repeat edits of configuration files, for example, on each and every instance. So here comes the deployment server, which allows to more easily distribute this configuration to groups of Splunk instances. A possible topology is the one shown here. This is also typically what you would prefer to do every time you get the chance, depending on the volume of the deployment. So final user search jobs are load balanced to a search head cluster with captain and workers, managed by a deployment server. Search jobs are then distributed to an indexer cluster. Here, the relation typically advised would be one search head to 7 indexers. So in most small deployments, one search head is enough. And finally, we have a set of hundreds of forwarders, typically universal, with load balancing in front of the indexers. So here is something that is common in the Splunk space, but should be avoided whenever possible. This is what we call a bridge topology. There are two heavy forwarders in front of the indexers, and the universal forwarders send data not directly to the indexers, but to this heavy forwarder. This can be done for a lot of different reasons, some of which can also be sort of reasonable. The problem here is that this creates a bottleneck. Even in a multiple routing scenario like the one you see here, it creates data ingestion. Because at any point in time, there will be like you see, there will be indexers overcharged and other indexers underutilized. So this can be somewhat mitigated by increasing the number of heavy forwarders, but at the expense of a heavier footprint. And this scenario is used most likely when we need some advanced filtering, routing, or other type of elaboration on multiple related sources of data before indexing it. A preferable topology is this one, that is a flat one. A huge set of forwarders pushes data directly to indexers, avoiding data congestion and minimizing footprint. Most of the architectural and managing problems of Splunk Enterprise, that is the on-premise version of Splunk, can be sidestepped with Splunk Cloud. With Splunk Cloud, basically, we can worry about just the bottom part of the architecture. So if we see the topology again, we can just care about the bottom part, so the forwarders, because the rest is taken care of by the Splunk support team. So everything up from the indexer to the search head cluster. And these dramatically decrease time to action, often allowing to productionalize a dashboard in a matter of hours. Upgrades changes are also taken care of by the Splunk support team. And other advantages, as you see here, are the adaptive data capacity, the Splunk-based cloud apps, which usually take priority on their enterprise version, for example. This is because Splunk is adopting a cloud-first approach on all of its solutions. So this embraces, well, the general sentiment of the market. And you also get advanced Splunk solutions, or like they're called premium apps, like Splunk IT Service Intelligence, Splunk Enterprise Security, Splunk Behavior Analytics, and so on. And finally, another advantage is the Splunk IDM, Input Data Manager, because it's a fast and easy to use cloud-to-cloud data ingestion solution. So that, for example, any type of AWS or Azure logs can be ingested into Splunk, typically more easily than custom data from on-premise servers. We're ready to discuss the Splunk pipeline. As you can see, there are 6 steps: forward, index, search, data enrichment, dashboards, and alerts. Ingesting data in Splunk can be done, as we said, with forwarders, and there are 2 types. A universal forwarder is what you would typically use in most scenarios, since it's lightweight, it does what it needs to do, it doesn't parse data, doesn't do any kind of elaboration that anyway you won't need to do, because the preferable approach is to index whatever and then use the Splunk machine engine for elaboration. In some use cases, The use of a heavy forwarder, though, is mandatory, and is one of the most frequent examples. Fetching data from relational databases like Oracle or Postgres instead of syslog requires a heavy forwarder. So what is a heavy forwarder? It's just a full Splunk instance, so it can do basically what Splunk can do: index, search, and parse data. It's worthwhile to notice that all Splunk apps related to data ingestion, for example, require a heavy forwarder. For index, we mean two different things. So one abstract and one practical. From an abstract point of view, an index is a logical grouping for data to be referenced in a search. For a more technical viewpoint, an index is something that consists of many time series index file that we will later talk about. According to source types, an internal special field that is very important is the underscore time field. This gives an automatic chronology to our events, that is a history of our logs. Here on the bottom, we see the inclusion diagram pertaining to indexers. So events are stored in buckets, which form indexes that live inside indexers. On the right, we can see the buckets. Buckets move to different life stages in their lifetime, just like us. So youngest buckets are the hot ones where we write data and that are available for searches. And then with the passing of time, they become cold and then frozen. So not all the type of buckets are shown here for lack of space. And the important part here is that hot buckets make searches faster by using the Bloom filter, a technique that we will later see. This is the more technical description of what's inside a bucket. So the most important file is the journal.gz file, where all the events are compressed and stored. From the raw events, unique terms are selected and then written to the lexicon. The lexicon is just a mapping of term to position in the events array, what we call a posting value. And then we look up the posting list, which is a mapping of the posting value to the seek address. The seek address is where we can finally find the event in the journal.gz file. So this can be quite confusing. So let's visualize it with an example. Since in a few minutes we will talk about Bitcoin transaction, let's keep the example on this topic. Let's say our raw events just keep track of these transactions. So we have John sends 1 Bitcoin of data, sends 1 Bitcoin to Mark, Kate sends 2 Bitcoin to Luke, and so on. What we do is map each unique term that is important, that is unique, to where it appears in the events list. So the posting value list is just an array of numbers. So for example, we see that sends appears in all 3 of the events. So we put 1, 2, 3. 2 appears only in the event number 2. So we put 2, and so on. And then to each of these entry, a seek address is provided that tells us where to look for that word in the journal file. Finally, we can create our first search. So sorry for the image here, it's a kind of deformed. This is a simple sample search that searches the number of logs by status of the internal Splunk index. And in the internal Splunk index here, in particular, we have the get API calls. So we can see here there are 2 parts. The first part is composed of base search commands, and this is how you typically start a search. It's a bit like using Google or grep, if you will, typing directly words or key value pairs in the search bar. And the second part is composed of SPL commands. SPL stands for Splunk Processing Language. It's the only language in which we will be able to write queries in Splunk. It's not a full imperative or functional programming language, so we can do whatever we'd like to do. For example, iterative pipelines are quite hard to implement, but for most stuff, it makes writing query very easy. It's to be thought as the Splunk version of SQL. We can see here we have 2 commands. one which creates or evaluates, as per Splunk terminology, a new field, and one which aggregates a count metric by another field. Here, the stats command is a generic command for computing aggregated statistics, and the last command is basically a SQL group by. On the right, then, there's the time picker, which selects the time frame for the search, and it's basically a filter on that special underscore time field that we saw. There are a lot of useful predefined options for the time picker, as well as custom settings, so it is very easy to use. In order to understand what makes Splunk scalable and fast for big data, we have to delve a little deeper into its inner workings, and particularly on how searches work. There's a little trick that makes searches very quick and convenient, and it's called the Bloom filter. So, well, let's reference the first part of the search. So I will go back just for some seconds. The first part of search is this: index equal internal, method equal get. So what we have to do here is that we have to find the logs with the field method value of get. So what we do is that the term get is run through a set of hashing functions, and each hashing function lights up one bit of an array, and this array is called the Bloom filter. So in this case, the Bloom filter is this one, 010000100. And each bucket has its own Bloom filter that we can imagine as a sort of label or stamp of the bucket, which is built with the same method applied to all words that appear inside the bucket. And it is crucial here to observe that false positives are possible, but false negatives are not. This is because if a word appears in a bucket, the Bloom filter of that bucket will have at least the bits related to that word equal to 1. Neither of these can be equal to 0. But on the other hand, if it doesn't appear, this word in the bucket can still have those bits equal to 1 because they might be lighted up by other words. So in our case, we will check only the second and third bucket, but maybe only one of them may contain the word get. Then we locate the value get in the time series index files, and as usual, we retrieve the events with get using the address to the journal file. This is how distributed search works. So search head parses search into distributed and centralized parts. Distributed parts of search are sent to the indexers. Then indexers fetch events from disk, and schema is applied to the events. Here, by schema on the fly, we mean that schema is discovered at query execution time. Events are then filtered based on key value pairs. Distributed commands are applied. Results are sent to the search head. And then the search head applies centralized streaming and transforming commands and then displays the result. So SPL commands are divided into two groups. We have streaming and transforming commands. Within the streaming commands, we have two types, distributed and centralized. The distributed commands, which are also called eval commands, operate on individual events. So that's why they can be distributed. Examples are eval, which creates or modifies fields with formulas, regs for selecting regular expression, where for filtering, and so on. Centralized commands, on the other hand, they're also called streaming, stateful streaming because they retain the state of the query, and they run on the search head since they can't be distributed to search peers since, well, they don't operate on the whole result set, but on a subset. So stream stats is the most, let's say, it's the most illustrative example. It is similar to stats in the sense that it computes aggregated statistics on search results, but it doesn't work on the whole result set. It works on each event at the time the event is seen. For example, what we can do with stream stats is computing the average of a field over the last 10 events or over a time window. The other group is composed of transforming commands, and they are the last step in the search pipeline. So they aggregate on the entire dataset on the search head. And examples are stats that we've already seen, or top, rare, which selects the most or least frequent events, and so on. So let's practice what we've seen with a use case on COVID-19 tweets. Let's imagine that we have a data set composed of tweets on COVID from the last year, with fields like number of follower, text of the tweet, user description, location, and so on. So here is the Splunk search page. As you can see, we've indexed this data on the main index, and the host here is Twitter. We can see a number of information here. We can see we have 118 events with time frame year to date. And on the left, we have two lists, selected and interesting fields. So interesting fields are fields that are present in more than 20% of the events, and selected fields by default are just three standard ones, so host, source, and source type. We can select fields that we care about from the interesting fields. So like it's shown here, for example, for the field user description, we can see also that Splunk makes our life easier because it shows the most common values of a field with their count and their frequency, and also the sample text. For example, we can see here, I know the derivative of e to the x, okay. And then here we've elaborated a bit on the search. So we're searching for tweets mentioning the word China virus, and we get a preview of a timeline view. And bear in mind that we haven't used any visualizing command, so very useful. And this timeline is also clickable to zoom in on specific periods. And on the left, we now have a list of all the fields we deem important for us that we have previously selected. This is how simple it is to do some sort of rudimental sociopolitical analysis with Splunk. I won't delve into the single commands here, but the gist of it is that we're searching for the most frequent words appearing in the user description of users who use the term China virus in their tweets. And there's a filter to leave out words like and, is, and so on, just words that have less than 3 letters. Of course, there's a better way to do it with natural processing language, but that's out of scope for this talk. And the results here are quite interesting already, although not unexpected, because they kind of paint a picture already of the category of user who is probably a rightist, Trump user. We see MAGA, we see an appeal to patriotism, perhaps with country, and to the enemy with communist. And we also see a misspelling of Fauci. So there are definitely some things not to do with Splunk search, and they are summed up here. Just because you can doesn't mean you should. The first order of tips is to reduce data processed by Splunk, while the worst idea in this sense is to use index equal to all. Here, the asterisk stands for all, or to select all time on the time picker. Index, which tells me which bucket to search in, and the time picker, which tells me which part of the time series index to search in. Wildcards, which are these asterisks that you see here, enables us to search for prefixes or suffixes, but they're not to be overused. So this is because wildcards won't allow us to use the Bloom filter that we saw, and so they force us to search in each bucket. In this sense, of course, wildcard prefix are worse than wildcard suffix, since in the first case, we have to basically search for all the terms in the bucket, and it's the same as using a pure wildcard. Splunk search architecture is made for affirmative searches. So instead of searching for a value not equal to some other value, it's always better to list all the excluded values with and or. And finally, real-time searches are also very demanding and should be used sparingly. The second order of tips is to optimize distributed search. Of course, you should put distributed commands before centralized commands, otherwise it kind of defeats their purpose. And since once a centralized command is executed, the rest will be executed on the search head. This is the simple reasoning. So Splunk has 3 main modes of search that you cannot see here. I just put smart mode, but they are fast, smart, and verbose, and they all can be selected through UI. So they're all useful for different purposes. Fast search, for example, disables automatic field extraction. So the only standard fields the only fields highlighted are the standard fields. And it's useful when we just want the raw data without caring about much else. Verbose mode is kind of the opposite because it gives emphasis on the completeness of the search. So completeness of the search, but at the cost of speed. And automatic field discovery is always turned on with verbose mode. Even when we launch a stats command, for example, we can see the underlying data with verbose mode. Smart mode is somewhere in between verbose and fast, so it usually gives the best outcome. In smart mode, automatic field discovery is turned on only when you don't use statistical commands, so only when you search only with search commands. The transaction command, on the other hand, aggregates multiple events into one, and it does so according to a specified time frame. Often, it is mistakenly used to do some simple aggregation that can be done more easily with the stats command. So it should only be used when you really need to set the time boundaries of a list of events. And the last point here has more to do with the shift of mentality or philosophy, if you want. The old database mindset is to map entities to tables and then join all the tables containing the information we need. But in Splunk, we don't really have tables, so a join first mentality can be suboptimal. We are better off thinking about logs and how they can be put together with the simple or on source types. Up until now, we've mainly talked about the technical point of view of Splunk. Uh, a word is in order for the more business intelligence type of viewer. Splunk has a lot of tools that make it possible to create views, reports, dashboards uh, without having a coding knowledge by, for example, pivoting on datasets. So we will talk about how to enrich data in general, and then see how this can be used by basically everyone to produce compelling visualization. This is a view of the different knowledge objects of Splunk. Field aliasing is all about referencing fields with different names. Calculated fields are just a result of eval expression, which can be reused. Lookups are configurations to add fields from a table with fields matching one or more fields from the events. This is where you would actually use joins, but lookups are usually small, so small static files that might contain, for example, the location of the countries of the world or the registry of the different sections of a company and so on. Event types are a way to categorize a certain set of events selected through a search string with a field value pair. And finally, tags are just keywords that make it easier to search for specific events. All these tools can be leveraged with data models. Data models enrich data and enable users to autonomously create dashboard by just pivoting on data sets created by the technical people. So there's no need to design searches on this level. The pipeline is this. The so-called Splunk knowledge managers, that is anyone who knows SPL, create data models using all the tools we saw. Uh, and then what really is a data model? Data models, as per the docs, is a hierarchically structured search time mapping of semantic knowledge about one or more data sets. But what does it mean? Well, it is more usefully thought of as the Splunk version of a database schema. So then another user can use this data model to create reports just from the UI. It is worth pointing out that Splunk knowledge managers need to have domain and data semantics knowledge alongside technical knowledge in order to create data models. Datasets are the building blocks of data models. They have two properties, as you can see here. Hierarchy, so we have root and child datasets, and children on their own can have other children, just like real life. And inheritance, so all the properties of a parent dataset are inherited from its child through the use of constraints, also like real life, more or less. And a constraint is just a search that determines what is the child dataset. So it determines what is it through filters. There are three types of datasets. Events is the most basic one. We just build a constraint with key value pair searches. Search dataset, in the search datasets, we can customize the search. And in transaction in a transaction dataset, we can only use search built up of transactions. So let's go back to our COVID tweets. Here we have an example of a data model built out of datasets from the COVID tweets data. On the left, we can see the root events dataset, all tweets, and then under it, it's children dataset. So we can have, for example, only verified, popular users, new users, old users, and US users. On top, we see the constraint used to build the root dataset, and on the bottom, the selected fields for the dataset. And as you can see, there are different types of fields available to be added. So the normal fields, that is the auto-extracted one, the eval expression, the lookup, and so on. In this way, someone who only wants to work, for example, with popular users can wish to do so without coming up himself with search strings. Once someone created that data model, we can pivot on it. So we have the usual split rows, split columns, and metric parameters. And in this case, we want to see, for example, the number of tweets by location for popular users. And on the left, as you can see in black, we already have a list of possible visualization. So all these different functions can be done just by clicking around. So let's suppose we want a bar chart of the number of tweets during the previous year in Italy. Here is what it would look like. And as you can see, we have different match options for filtering that is just, let's say, out of the box and can be done through UI. Here is a somewhat more elaborated example in which we split by rows, columns, and we track multiple metrics. So what is interesting here is that some of the metrics are pre-populated just by the Boolean combination of root and children datasets that we've created. So they sort of come for free. Now, let's get to one of the central parts of using Splunk, that is dashboards. Dashboards are mainly used to have a live, holistic view of all the aspects that we want to track. So all the classical visualizations are available. We have line charts, we have area charts, bar charts, pie charts, and so on. But there are also some advanced ones possible with commands like geostats, which makes it possible to visualize pie charts or differently shaded areas, what is called a choropath map, on top of a word map. So in this way, we have a sort of geographical view of the data. Or we could just keep the visualization to a minimum and just have a glass table of service health indicators for monitoring reason. And for most purposes, everything can be done directly on the UI, but it's possible also to edit a dashboard, edit directly the XML of the dashboard. So let's create a mockup of a dashboard with the usual Twitter data. Adding panels to dashboard is very easy. As you can see, it's done directly from the search page by saving searches as dashboard panels. So once some panels are added, the dashboard will look something like this. Here, for example, we have a time chart of number of tweets and the average number of followers of the user creating the tweets, a bar chart of the top user, and a pie chart of the number of user per user type. Here, the user type is verified or not verified. So something like this can be created in a matter of minutes. The more a dashboard is dynamic and the more useful it is, a host of different inputs can be created, as you can see here on the left. Searches are then edited to make sure that we are using the input, the newly created input. So here we're creating a text input that accepts any type of word and filters only the tweets containing that word exactly or as a prefix. The final view of the dashboard might look something like this. This makes it immediate to, for example, have a view of all the different panels for a specific dashboard, for a specific time frame, in this case, before August 31, 2020, in New Delhi, India, containing the word death, for example. So a dashboard can be made even more dynamic by creating drill downs. Drill downs are context-aware secondary searches that run on top of the dashboards, allowing user to get a deep, dynamic, zoomed-in view of the data. So let's suppose that in the dashboard just created, we want to have a list of the actual tweets for April 2020. So I will just go back for a moment. So let's suppose that we just want that data, and not only, but we want to be able to do that by just clicking on the bar corresponding to the month of April. This is possible, and the final information can also take any form. So we can link to searches, we can link to reports, to other dashboards, and also to websites with to general websites. So clicking on this bar, we see we have 10 events, so we should get 10 tweets, and we actually have it. So we got the list of COVID tweets coming from New Delhi, India, containing the word death from April 2020. And this is a link to a search since we get the raw events, but it's not that clear for a non-technical final user. So what if we want a drill down table view? So the drill down search can be modified in order to achieve this. Here, if you look at the search string, the first part is just a basic search. And the second part, the one that starts with user underscore name equal to $click.value $, filters based on the bar that the final user clicked. So then we have the table command, which just selects the field we care about and displays it in a table format. So the result will be this, which is much more cleaner for a final user. The last step of this abstract pipeline deals with alerts. Alerts are actions triggered by a saved search meeting specific conditions. So this is a list of parameters to populate when we want to create an alert. The frequency of an alert should be chosen based on the use case. So for example, a saved search might be used for business goals. These are typically holistic alerts, monitoring the general health of an IT system. A real-time alert is a critical alert, so useful for immediate monitoring of crucial functions. And a rolling time window alert should be used when we need a specific time window, like counting the number of errors in the last 5 minutes. A trigger condition is a secondary search running on top of the alert search, which causes an action only when it produces results. So triggering can be per result or customized with this search. And throttling allows us to avoid spam by controlling how soon the next alert must be triggered. So we can also track trends over time with throttling. And then finally, an action is what happens once an alert is triggered. So we can send an email, update the general web resource with the webhook action, writing the result to a CSV, and so on. So talking about scheduled alerts, a scheduled alert is just like a scheduled report. The difference is that with reports, we don't have control on the trigger of the action. They just trigger each time they run. While scheduled alerts only initialize alert when they're triggered. We've praised Splunk highly enough, so let's look at what might be the bad part of using it. For sure, compared to the open source and closed source alternatives, it has a pretty high cost. Also, SPL is not everyone's cup of tea. It makes simple super simple, yes, but complex queries are quite hard to implement. For example, as we mentioned, there's not really a way to make an iterative process, although there exist some workarounds which are quite complicated. These and other things will make you want to, just write everything in Python. A lot of useful Splunk add-on and apps are not officially supported, and even when they are, integration with some data sources is sometimes suboptimal. There's not a default way of saving state between queries. Even here, there are some workarounds like indexing query, like it's just some logs, but it's not supported out of the box. And finally, It is sometimes hard to deal with configuration files since there are a number of different places to configure things and it's hard to know what goes where. So, what are the next steps with Splunk? There are a lot of Splunk premium apps for different use cases, machine learning, observability, monitoring. Here, we will just have the time to talk about the first one, so machine learning. The machine learning toolkit is, as I said here, machine learning for the people, since it's an app that allows to create, validate, manage, and operationalize machine learning models within UI with no code required. So it achieves this with specific SPL commands for machine learning that run on the background, the usual one like fit, model, and evaluate. And it also has custom visualization assistance as well to guide us through our first ML models and examples. We have all the typical algorithms like regression, classification, forecasting, and so on. But it is also possible to use open source Python algorithms or just build your own. So, as we mentioned in the agenda, let's now consider a data set of Bitcoin transaction. So if you don't know what Bitcoin is, it's not really important to know what it is in this context. Let's just say that it's a digital currency with anonymous participants, let's say. So coins are created or mined by miners, while regular users just participate in this game by creating transactions. So there's also exchanges, which are big players that exchange fiat currencies like euros or USD to bitcoins. But our goal here is just to predict from this data for each user, its user type, that is, if he's a miner, if he's a standard user, or if he's an exchange, or so on. Here's a glimpse of the dataset. For each wallet address that is user, we have a label of its user type and a bunch of features of that user, like what is the average volume of its transaction. We might expect, of course, that a higher volume of transaction is a strong hint that we're at the presence of an exchange, for example. This is the model assistant for the machine learning toolkit that illustrates quite well how easy it is to leverage machine learning, albeit in an experimental way, for our data. We first select the search, which produces the dataset, and then the algorithm and hyperparameters. Here we use the random forest classifier. Then we choose the field to predict, which is in this case just the label of the user type, and the features to use for predicting. And we finally select the training test split, and we have the option to set some advanced parameters or pre-processing steps. Then we just click on Fit Model and let the magic work. So we can look at the prediction results for each event that are highlighted here. Well, in green, you can see that are highlighted all the inputs which were not predicted correctly. We have then a view of the evaluation matrix and the confusion matrix. We can expect, for example, that it's harder to distinguish an exchange from a miner. Then, for example, it is to distinguish a miner from a regular user, since exchanges and miners are both big players in the Bitcoin world. So finally, we can click on Show SPL to see what it is the SPL equivalent of this UI process. And the syntax, as we see here, is very simple. We feed the algorithm to the field to be predicted from the predictors and save it into a draft model that we name, and then we apply that model to the dataset. To compute the evaluation matrix, we pipe that into a multi-report and use the score command to compute the various matrix, or the confusion matrix macro to compute, well, the confusion matrix. So finally, here are the key takeaways from this talk. The Splunk holistic model is more suitable to face and solve modern problems with big data. Flat topology should be preferred for data ingestions. Universal forwarders should be used instead of heavy forwarders whenever possible. Splunk Cloud is on average better than Splunk Enterprise for most scenarios. Make a smart use of indexing and distributed computation workflow. Create data models to allow stakeholders to independently work with data and create dashboards and alerts in a matter of minutes, and then accelerate productionalization of machine learning models without knowing a single line of code. So the last point is a sort of paradigm shift because it might raise some eyebrows, but I think it's worth pointing out that Splunk surely allows this more, let's say, reckless approach. And it has some upsides as well, like boosting a more creativity approach to our data. So here are just some resources for further reading. So if you want to delve deeper into Splunk Cloud or the premium apps, the additional products of Splunk, like Splunk ATSI, we have also customer stories and additional resources if you can find something that is not listed here. And then a link to the official documentation. Of course, the most important one of this is the public forum, where if you have a question, probably it's already answered there. So thank you for the talk. And well, as last words, I would like to remind you that you can hit up that survey button that's on the top of the live. I think that feedback is important for us as well for you, for the bettering of the event. And then I can invite you to the table section where you can just chat. We can just chat, or you can ask me questions. So goodbye.